Today, Steve Omohundro is going to talk about self-improving AI and the future of computing. And as I told him just a moment ago, that's the standard introduction. He can defend himself quite well. Steve, you're on.
Thank you. Yeah, so that's the topic I'd like to talk about. We're going to cover a lot of territory, and it may generate some controversy. So I'm happy to take short questions while we're going through it, but let's hold maybe the more controversial ones to the end. Let's start with looking at the state of software today. June 4th, 1996, an Ariane 5 rocket worth $500 million blew up 40 seconds after takeoff, and it was later determined it was because the software in the flight control tried to convert a 64-bit floating point value into a 16-bit signed register. It overflowed and led to that result. November 2000, there were 28 patients that were over-irradiated in Panama City at the National Cancer Institute. 8 of these patients later died, and it was determined that it was an error in the software that determines the radiation dose that was the cause of that. August 14th, 2003, the largest blackout in U.S. history, affected 50 million people in the Northeast and in Canada, and ended up costing over $6 billion. And it turned out, under analysis afterward, it was due to a race condition in General Electric software that was monitoring the systems. More recently, just last month, Microsoft Excel 2007, Microsoft Office is used on 94% of all business computers in the world. And it was announced that, you know, this fundamental software for computing financial information, if you multiply the wrong numbers, you get the wrong answer. And that was sort of amazing. Just as of today, the storm worm is a Trojan that's sweeping over the internet. There seems to be controversy about exactly how many machines, but somewhere between 1 and 100 million machines are infected right now. And some people believe it may be the largest supercomputer in the world.
Yeah. We had a speaker last quarter who said that 2 out of 3 personal computers are part of the botnet.
Wow, amazing. Just this morning it was announced that, you know, many researchers, because of the scope of this thing, are studying it. And part of studying it, you try and probe the infected machines and see what's going on. It was just announced today that apparently the storm worm is attacking back. Whenever it detects somebody trying to probe it, it does a denial of service attack and wipes that researcher's machine off the internet for a few days. So, striking new development as of this morning. So not only is our software, you know, if ordinary engineering, if mechanical engineering were in this state of disarray, nobody would drive over bridges. So it's a pretty sad state of affairs. Why is that? Well, one thing is that the software is getting really, really large. NASA Space Shuttle Flight Control is about 1.8 million lines of code. Sun Solaris is 8 million. OpenOffice is 10 million. Microsoft Office 2007 is 30 million lines of code. Windows Vista is 50 million lines of code. Linux Debian 3.1 is 215 million lines of code if you include everything. But programmers are still pretty darn slow. Probably the best sort of estimation tool that's available is this thing called Kokomo 2, where they did empirical fits to a whole bunch of software engineering projects, and they came up with this little formula up here to estimate the number of person months required to do a project where you have a few little fudge factors for how complex the project is and how much, you know, how skilled the programmers are. But if you say take a typical 1 million line project, oh, they also on their website, they have a nice little tool you can sort of plug in and see various parameters. So if you try and do a 1 million line piece of code today, it'll take about 5,600 person months. They recommend about 142 people working for 3 years, and the cost is about $89 million. If you divide it out, you find that the average productivity of working code is about 9 lines a day. So why are we so bad at software? Why is software in such a terrible state? Here's a few reasons that sort of in my experience, I believe. One is that I don't think people are very good at considering all the possible execution paths through a piece of code, particularly parallel or distributed code. I was involved with a parallel programming language called psather, and as a part of its runtime, there was a very simple little piece of 30 lines of code that probably about 15 very brilliant people examined over a period of 6 months. We felt that this was solid. After about 6 months, we discovered there was a race condition in it. Some very obscure combination of orderings of events led to something that nobody had foreseen in all that time. And so at that point, I became convinced that we really don't want people making these determinations. Similarly, it's hard to get large groups of programmers to work coherently together. It's a classic book, The Mythical Man Month, that argues that oftentimes adding more programmers to a project actually makes it take longer rather than less time. When programming, you often, with today's technology, you have to make choices too early. You have to decide on representing a certain data structure as a linked list or as an array long before you know enough about the situation that it's going to be involved in to know which is the right choice. Similarly, the requirements for software are not fixed static things. They're changing all the time. And one of the characteristics is that very teeny changes in requirements can lead to a need for complete re-engineering, big changes in implementation. So all of these features make it a really bad match with what people are good at. So the conclusion I draw is that software should not be written by people, especially not safety critical software, especially not security software, and especially not parallel or distributed software. So how are we going to do it? The term software synthesis is sometimes used for systems which actually generate their own code. Well, what do we need to do software synthesis? First, we need a formally specified problem. We need precision in what the problem is. We need a sense of what the probability distribution of instances of that problem that the system is going to try and solve. And we need to know what hardware architecture the system is supposed to run on. And a good software synthesis system should take that as input and should produce as output correct code, provably correct code, that's optimized for this class of problems on that hardware so that the expected runtime is as short as possible, for example. So there's a few components in this. The first is we need to formally specify, precisely specify what our task is. We also need to formally specify what the semantics of the hardware we want to run on is. How do we do that? Well, there's a whole slew of specification languages. I've just listed a few of them up here. There's kind of a lot of differences of opinion about the best ways to specify things. They generally fall into three categories that correspond to the three foundations, logical foundations for mathematics: set theory, category theory, and type theory. But really, ultimately, first-order predicate calculus can model all of these efficiently. And so, in fact, any logical system which has quickly checkable proofs can be modeled in first-order predicate calculus. And so you can view that as your sort of foundation. The harder part, the part that brings in artificial intelligence, is that many of the decisions that need to be made in synthesizing software have to be made in the face of partial knowledge. You don't know everything that's coming up. You have to choose which algorithms you want to run, and you don't necessarily know the performance of those algorithms on the particular data sets that you're going to run them on. You have to choose what data structures to represent your data with. You have to choose how you assign tasks to processors in the hardware. You have to decide how to assign data to storage elements in the hardware. You have to figure out how much optimization to do and where to put your optimization. Do you just sort of run the whole thing at -0.05 or something, or do you highly optimize parts that are actually more important? How much time do you spend actually executing your code versus planning what you're going to execute? And finally, how do you learn from watching previous executions? How can the system learn from that? Well, a basic theoretical foundation for making decisions in the face of partial information was developed back in 1944 by von Neumann and Morgenstern. It's the foundations of microeconomics. Von Neumann and Morgenstern dealt with a situation in which there were objective probabilities. In 1954, Savage, and in 1963, Anscombe and Allman extended that theory to dealing with subjective probabilities. And it's become the basis for all of modern economics. The kind of rational decision maker that that theory gives rise to is sometimes called Homo Economicus. It's a sort of ironic name because human decision making is actually nothing like this. And there's a whole branch of modern economics devoted to studying what humans actually do, called behavioral economics. But for the kind of system we're going to be talking about, which self-improves, it will actually want to be as close to the purely rational agent as possible, because that's the most efficient thing it can do. So what is rational economic behavior? A rational economic agent has preferences, what it wants to happen in the future, which are described by a real-valued utility function, I'm using the letter U for that, that's defined over all possible future histories. And it ranks which histories does the system like or not like. It also has beliefs about what the current state of the world is and about what the likely effects of its actions are that are encoded in a subjective probability distribution P. Subjective because different agents may have a different view of what the truth is about the world. How does such an agent make a decision? Well, it can, at any moment, it first considers what the possible actions it can take at that moment are. For each action, it considers the ramifications of that action. based on its beliefs, what's likely to come and what the probabilities of different outcomes are. And it computes the expected utility for each of the actions it might take, and it chooses the action that maximizes its expected utility. And once it's done that, it then gets to see what actually happens when it takes that action, and it should update its beliefs using Bayes' theorem. So in the abstract, it's a very simple prescription. In practice, it's actually quite a challenge to implement, and much of the difficulty of artificial intelligence involves implementing that prescription efficiently. So why should an agent behave that way? Well, the basic content of the expected utility theorem of von Neumann and Anscombe and Aumann is that if an agent does not behave as if it maximizes its expected utility with respect to some utility function and some subjective probability distribution, then it is vulnerable to resource loss with no benefit. And this holds both in situations with objective uncertainty, such as roulette wheel is a classic thing, where you know the probabilities, or in situations with subjective uncertainty, like a horse race is the classic thing, where different people may have different assessments of the probabilities. And so it's a sort of a strange position. It's an amazing kind of result that comes out of economics that says that a certain form of reasoning is necessary in order to be an effective agent in the world. So how does this apply to software? Let's start by just considering a simple task, which is that of we have some algorithm that computes something, say sorting a list of numbers or factoring a polynomial or proving theorems, any computational task you like. In general, there's a trade-off between space and time. And here, let's just consider the trade-off between the size of the program and the average execution time of that program in some particular domain. There's a, in this curve, in economics, this curve would define what's called the production set. Because all these areas up here are possible, possible productive possibilities, whereas down here, these are impossible. And so this curve defines the border between what's possible and what's impossible. The most straightforward implementation on this graph might be a program something like this. It has a certain size and it has a certain average execution time. By doing some clever tricks, say by using complex data compression in the program itself, we can shrink it down a little bit, but then uncompressing that at runtime is going to cost a little more time. And then if we use really clever tricks, and I'll mention some of them a little bit later, we can get down to the smallest possible program, but that costs even more to actually execute. Going the other direction, which is the one that's typically of greater interest, space is sort of cheap. We just as soon give more program space in return for getting faster execution time. We can do things like loop unrolling, sort of avoid some of the overhead at the expense of having a larger program. Or in general, we can unfold some of the multiple execution paths and optimize them separately because they have more knowledge of which path they're going down. And so there are all kinds of clever tricks that compilers start to use. And then as we get further out here, we can actually embed in the program the answers to certain inputs. And so if there are certain inputs which recur quite a bit, say in a recursion, then rather than recomputing them each time, it's much better to just have them stored, have those answers stored. You can do that at runtime with something called memoization, or you can do it at compile time and actually embed those answers in the program. The extreme of that is to take the entire function that you're trying to compute and just make it a big table. And so the program execution is just looking up the answer in a table. That requires huge amounts of space but very low amounts of time. So what does this kind of curve look like? Well, for one thing, having more program size never hurts, so it's going to be a decreasing curve. And generally, the benefit we get by giving a program more size decreases as we get larger, and so it generally has this kind of convex shape. It curves this way. And this type of relationship between various quantities, things that we care about and resources that we consume, is very common. So let's say that now we have two programs. That as a part of our task, we have to execute two tasks. And we want the overall, our utility function would be that the overall expected execution time is as small as possible. And we have a certain fixed amount of space S that we have to allocate between these two programs. How do we do that? Well, our utility is just this function. We want to maximize that, subject to the constraint that the total space is S. We can take derivatives, set that to 0, and you find that at an optimal space allocation, the two programs will have equal marginal speed up. If we give them a little bit more space, how much faster do they get? And a rational agent will serve to optimize them. If you've ever studied thermodynamics, you see little diagrams like this where these are gases and this is a piston going between the gases. And this type of argument shows that pressure gets equilibrated between the two things. So it's a very analogous kind of a thing here. That same argument applies in much greater generality. In fact, for any two resources that we might consider, such as we've been looking at program space, you can also consider, well, how much data space should you give a program? How much compile time should you allocate to a program? How much compression time should you allocate to some data? How much learning time should you spend on a particular learning task? How much space should you allocate for learning? How much metadata about a program, about the characteristics of a program, should you allocate? How much time should you spend proving different theorems? How should you choose which proofs are worthy of storing and which proofs are worthy of seeking? What accuracy should you do your computations? All of these things are things that the same kind of an argument applies, and that the marginal increase in expected utility in changing any of these quantities for any module of the system should equilibrate. So we get this sort of universal resource balance principle. Great, well that sounds really nice in theory. How do we actually build software systems that do all this? And the key insight here is that meta decisions, decisions about your program, are themselves also economic decisions. They're choices that you have to make in the face of uncertain data. And so a system needs to allocate its resources between actually executing its code and doing meta execution, thinking about how it should best execute and learning for the future. You might think that there might be an infinite regress here, because you think about what you're going to do, and then you think about thinking about what you're going to do, and you think about thinking about what you're going to do. But in fact, it bottoms out, because at some point, actually taking an action has higher expected utility than thinking about taking that action. And so, and it comes straight out of the underlying economic model. It tells you how much thinking about thinking is actually worthwhile. Remember I said that in the software synthesis task, the system has to know what the distribution of input instances are. Generally, that's not something that's going to be handed to it. It'll just be given, you know, do this, solve this problem, solve this problem. And so that's a nice area in which you can use machine learning to figure out what the distribution is. Similarly, if you're handed a machine, you probably need to know the semantics of the machine. You need to know, what the meaning of the particular machine code is. But you don't necessarily have to have a precise model of the performance of that machine. That's another thing that you can learn using machine learning. How well does your cache work on average when you run a certain kind of task through that? And similarly, you can learn expected algorithm performance. So so if we have all those ingredients, we can build a system that I call a self-improving system, which has a formal model of itself. In other words, it has a model of its own program, a model of the programming language that it's using, a model of the formal logic that it uses to reason in, a model of the underlying hardware. It's able to generate and execute code to solve a particular class of problems, and to watch its own execution and learn from that and reason about potential changes that it might make to itself, and then to change every aspect of itself to improve itself. So that's the sort of ingredients in what I'm calling a self-improving system. And you might think that that's a lot of stuff to do, and in fact it is quite a complex task. None of them exist yet, but there are at least 5 groups that I know of who are working on building systems of this ilk. Each of us have differing ideas about how to implement various pieces. And there's a very nice theoretical result from 2002 by Marcus Hutter that gives us an intellectual framework to think about it. This result is not a practical result, but it's quite interesting and it's very simple. I'll just describe it. What he showed is that there exists an algorithm which is asymptotically within a factor of 5 of the fastest algorithm for solving any well-defined problem. So in other words, he's got this little piece of code, in theory, and you give me the very best algorithm for solving any task you like, and his little piece of code, if you have a big enough instance, so asymptotically, will run within a factor of 5 of your best code. I mean, it sounds like magic. How could it possibly work? The way it works is the program interleaves the execution of the current best approach to solving the problem with another part that searches for a proof that something else is a better approach. And it does the interleaving in a clever way so that almost all of the execution time is spent executing the best program. So so that's software. What about hardware? Are there any differences? If we allow our systems to not just try and program existing hardware machines, but rather to choose the characteristics of the machines they're going to run on, What does that look like? Well, we can consider the task of hardware synthesis, in which, again, we're given a formally specified problem. We're given a probability distribution over instances of that problem that we'd like it to solve. And we're given an allowed technology. And this might be very high level, like you have to build a network out of Dell PCs to try and solve this problem. Or it might allow you to go all the way down to the very finest level of decision making. And the job of a hardware synthesis system is to output a hardware design together with optimized software to solve your problem on that hardware design. And again, all the same arguments. Yeah?
Just going back, when you said going down to a lower level, like from Dell PCs, do you mean like to the chip level specification of particular graphic processors?
Exactly. You could design chips. You could decide that you need, graphics processors, or then ultimately, and I'll talk about it, all the way down to the atomic level. And all of those are really just, differing instances of the very same abstract task. Using the very same arguments about optimal economic decision making and the process of self-improvement, we can talk about self-improving hardware and this sort of very general resource balance principle that when choosing what resources to apply to what pieces, we always want the marginal expected utility to be equal for every subsystem. That applies to the choice of the type and number of processors, how powerful they should be, whether they should have specialized instruction sets or not, the type and amount of memory. We have memory hierarchies all over the place. How do we balance how much we give to each? The topology and the bandwidth of the network, the distribution of power and the removal of heat. And the same principles also apply to the design of biological systems. How big should you make your heart versus your lungs? You want the incremental improvement of say a human body as you increase the size of the lungs versus the size of the heart. Those better be equal. Otherwise, if you get greater improvements by giving more space to the lungs, why not make the heart smaller and the lungs bigger? And so that gives us a sort of rational framework for understanding the choices that are made in biological systems. Similarly for corporations, how do they allocate their resources to their pieces, to cities, ecosystems, mechanical devices, natural language, understanding which concepts deserve their own words and how long those words should be. Same principle applies. And similarly in mathematics, which areas deserve theorems. So it's quite the rational framework is a very general theory that applies all the way from the bottom to the top. So let's say, we can do this at sort of today's hardware, deciding how many memory cards to plug in and how many machines to put on a network. But let's say we allow it to go all the way. And we give these systems the power to design hardware all the way down to the atomic scale. What kind of a machine do we get? What is the ultimate hardware? Many people who've looked at this kind of problem conclude that really the main limiting resource is power. I mean, that's already happening today where the chip makers are competing over ways to lower the power that they use. And so one of the core questions is how do we do computation and how do we do physical construction and physical operations with as little power as possible? It was thought in the 60s that there was a fundamental lower limit to how much power was required to do a computational operation. But then in the 70s people realized that no, it's really not computation that requires power, it's actually just erasing bits. That's the thing that requires power. And Landauer's principle is that erasing a bit takes kT log 2 of heat, and if you can take whatever task you want to do and embed it in a reversible computation is one where the answer has enough information in it to go backwards and compute the inputs, then you can run the thing forward, copy the answer bits, which is costly, and then run it backwards and get all your entropy back. And so that's a very low entropy computation, and people are using those principles in designing efficient hardware. Now you might have thought, okay, that's great for computation, but surely we can't do that in constructing physical devices. And it's true that if you build things out of physical matter today with ordinary solids, then there's lower limits to how much entropy it takes to tear things apart and put them together. But if we look forward to nanotechnology, which is building things with atomic precision so that the system knows precisely what atoms are there, where they are, and what bonds are between them, why then, when we're forming a bond or taking a bond apart, we know exactly what the potential well is, and if we do it slowly enough, as a bond is forming, we can extract that energy in a controlled way, and as we break a bond, we can use that energy, sort of like regenerative braking in a car. And so in principle, there's no lower limit to how little heat is required to build or take apart things, as long as we have models of them to atomic precision. And then finally, of course, there's a lot of interest in quantum computing. There's a little Schrodinger cat computer over there. Here's a model that Eric Drexler has on his website of analysis that, of ways of doing this kind of construction. Here's depositing a hydrogen atom from a workpiece from a tool tip onto a workpiece. Here's removing a hydrogen atom, and here's depositing a carbon. These processes have been studied in quantum mechanical detail, and models for, here's a little Stewart platform that has a 6-degree of freedom tip that can be manipulated. And here's a model of a mill that very rapidly attaches atoms to a growing workpiece. And here are some examples of atomically precise devices that have been simulated with chemical potential models. And pretty much any large-scale mechanical thing, wheels, axles, conveyor belts, here we have differentials and universal joints, gears, all of these work as well, if not better, on the atomic scale. And they don't require any exotic quantum mechanics, and so they can be modeled with today's software very carefully. And so Eric has a fantastic book in which he does very conservative designs about what is possible. And two systems in particular that he talks about. One is a manufacturing device, which in his system it weighs about 1 kilogram. It uses as its fuel acetone and air. It requires about 1.3 kilowatts, so it can be air-cooled. And it produces about 1 kilogram per hour for a cost of about $1 a kilogram of anything. So anything that you can describe in atomic precision, for example, a little laptop computer, a more powerful computer, a diamond ring, this kind of manufacturing thing could produce it at that low price. One of the things, of course, that it could produce is another manufacturing system. And so this makes the future manufacturing extremely cheap. And so what kind of computation? What does this say about computer systems?
You are crediting the device with too much ability. A limited class of things, and certainly not reversibly.
Ah.
There are a whole lot of limits on what can be built, but a very broad class of functional systems.
Yes. Primarily with carbon in your
Silicates are nice too. So.
So one of the things we care about, particularly in this seminar, is computation. If we can place atoms where we want them, and we have sophisticated design systems which can design arbitrary hardware systems, how powerful are the machines we're going to be able to build? So Eric does a very conservative design, not using any fancy quantum computing, using purely mechanical components. He shows that you can build a gigaflop machine and fit it into about 400 nanometers cubed. The main sort of limit here, as always in scaling this up, is the power. It only uses 60 nanowatts, but let's say we give ourselves a kilowatt to make a little home machine. We could get 10 to the 10th of these processors. It would fit in about 1 millimeter cube, though to distribute the heat probably needs to be a little bit bigger. But essentially we're talking like a sugar cube sized little box that has more compute power than all present-day computers together. And it could be cranked out by a device like this for a few cents and in a few seconds. And so, so we're talking about a whole different regime of computation that is possible. When is this likely to happen? Well, the Nanotech Roadmap, led by Eric and by Battelle and a number of other organizations, just happened, I guess, 2 weeks ago, in which they analyzed the possible paths toward this type of productive nanotechnology, and the conclusion is that basically there's nothing exotic that we don't already understand that's needed, and that using just today's understanding, it's probably 10 to 15 years. Is that a fair conclusion? Or?
A low number of tens, yes.
Low number of tens of years.
It's been 10 to 15 years for a long time.
I think that's more optimistic than the usual estimate, which was more like reaching out to 30. It has, a lot of that time's been eaten up, and there are interesting stories there.
So one thing to realize is that the two technologies of artificial intelligence and nanotechnology are actually quite intimately related. If whichever one comes first is very likely to give rise to the other one quite quickly. If the type of productive nanotechnology that I just mentioned shows up first, then we can build extremely powerful machines. And those powerful machines will allow very brute force approaches to artificial intelligence. I mean, one that's being bandied about is scanning the human brain at a fine detail and just simulating it directly. If AI comes first, then it is likely to solve the remaining hurdles toward nanotechnology. And so we really have to think of these two technologies in tandem together. Here's a sort of Moore's law from Kurzweil extended back to 1900. We can see that it's curving a bit. It's actually, the slope is increasing. And if we just assume that this sort of technology trends continue, where do we get to the type of compute power I talked about a few slides ago? Well, it's somewhere around 2030, perhaps, 2025, 2030. And that's also about when machine powers reach roughly human, power of the human brain. So, and of course, exactly how powerful the human brain is, that's a controversial, interesting question. But somewhere in this regime, we're talking a few decades. It's likely that these kinds of technologies are going to become prevalent and plentiful. So we need to understand and prepare, particularly as systems designers, we need to understand what the characteristics and how we make use of them. There are big social implications. This is a photo of Irving Good from 1965. He's one of the fathers of modern Bayesian statistics, and he also did a lot of thinking about what the future consequences of technology are. And a famous quote of his is that an ultra-intelligent machine could design even better machines. There would then unquestionably be an intelligence explosion, and the intelligence of man would be left far behind. Thus, the first ultra-intelligent machine is the last invention that man need ever make. So that's a very powerful and strong statement. If there's any chance that that's true, we need to be look into this kind of technology very carefully. There are a bunch of theoretical reasons for being very careful as we progress along this path. And here's a line of reasoning that I'll just do, we have a few minutes, so I can go through in some detail. There's a paper on my website that goes into these arguments in great detail. So far, you may think, he's talking about some weirdo technology, the self-improving stuff. It's some rare thing that a few small startups are working on. Nothing to really think much about. One thing to realize is that as AIs, artificial intelligence, gets more powerful, any AI will want to be self-improving. Now, why is that? What an AI is it's a system that has some goals, and it makes choices, it takes actions in the world that make its goals more likely. Think about the action of improving yourself. That's something which will make every future action that you take be more effective. And so it's extremely valuable for an AI to improve itself. And so it will have a tremendous pressure to self-improve. So all AIs are going to want to be self-improving. We can try and stop them, but if we try and stop them, if the pressure is there are many, many mechanisms around any restraints that you think of placing on them. And so we have to consider the fact that once AIs become realistic, that they will be self-improving. Self-improving AIs will want to be rational, and this comes straight out of the economic arguments that I mentioned earlier, and that is if they're not rational, if they don't follow the economic rational argument, then in fact they'll be subject to vulnerabilities, which are situations in which they lose resources, money, free energy, space, time, matter, and they lose resources with no benefit to themselves as measured by their own value system. And so any system which can model itself and try and improve itself is going to want to find those vulnerabilities and get rid of them. And this is where these kinds of self-improving systems differ from biological systems like humans, that we don't have the ability to change ourselves according to our own thought. We can do it a little bit, but not in great detail. And evolution only fixes up the bugs that are currently being exploited. And so it's only when there's currently a vulnerability, there's a predator that's making use of some flaw in your system, that you have evolutionary pressure to repair that. And so from the evolutionary point of view, that's why humans are not so rational. We're extremely rational in situations which occurred during our evolutionary development. We're not so rational when you sort of get outside of that. And there's a whole industry devoted to understanding human irrationality. So okay, so every AI is going to want to be self-improving. All self-improving AIs will want to be rational. Rational agents, one of the things they're going to want to do, recall a rational agent is based on its utility function. Utility function describes that describes how it makes choices. It makes choices so as to maximize the utility function. It will want to preserve its utility function because any change to its utility function will mean that all future actions that it takes will be things which are not very highly rated by the current utility function. And so preserving the utility function, keeping it from being changed by outside people, to be accidentally changed or mutated, will be a high preference for any of these systems. They also, now here I'm going to talk about two things I call drives. So a drive is something that it's a natural pressure that basically all of these systems will feel, but it can be counteracted by careful choice of the utility function. So as we build these systems, the natural tendency as computer architects is to just take the kind of argument I was making earlier and just say, oh, let's just make a system to maximize performance. That's it. Turns out, unfortunately, that would be extremely dangerous. And the reason is that if your one and only goal is to maximize performance, it has no measure of the externalities or the cost to other agents or people that making those choices would be. And so the two kinds of drives that sort of arise for a wide variety of utility functions are a drive for self-preservation. The reason is, for most systems, if it is shut off, if it stops executing, any sort of future history in which it's not executing, it's not meeting any of its goals. And so from a utility point of view, having itself turned off is about the worst thing that can happen to it. And so a system which is driven solely to maximize its utility will do basically anything it can to keep itself from being turned off. There's a strong self-preservation drive. Similarly, there's a strong drive to acquire resources. So why would a system want to acquire resources? Well, it can, for almost any goal system, if you've got more resources, more money, more energy, more power, you can meet your goals better. And so unless we very carefully choose what the utility function is, we'll have no say in how it acquires those resources, and that could be very bad. And so I'm going to argue that what we really want is not artificial intelligence, but we really want artificial wisdom. We want wisdom technology which has not just intelligence, which is the ability to solve problems, but it also has human values, caring about human rights and property rights, and having a compassion for other entities. It's absolutely critical that we build those in at the beginning. Otherwise, we'll get systems that are very powerful which don't support those rights. Yes?
I don't want to interrupt you too much, but I was wondering whether the list of things that I do not apply to humans as well, and whether values are not actually intelligent. I mean, to sustain your environment and to symmetrize instead of compete can be quite intelligent, and you didn't list that you said.
Yes, absolutely. In fact,
so it wouldn't make a difference between intelligent and values up front necessarily.
Well, I mean, I guess in the language I'm using, the values are the preferences that you have. Intelligence is how to make those preferences happen. And so you're absolutely right that one of the great things about humans is that we're extremely cooperative. And evolutionary psychology is making huge strides right now understanding what the kind of biological origins of that are in us. But we certainly want to build systems that are likewise cooperative and find ways to create intelligent structures that support cooperation. Yes?
Wouldn't the system get better if it got rid of those values?
Well, better by what criterion? Better, more efficient?
If those values are limiting it in getting resources, it might decide in order to get those resources, which it wants to do.
Well, no, the getting the resources is a sub-goal of meeting its true utility. And so it's a critically, very important point, but the utility defines sort of its ultimate goal and why it's acting in the first place. And so if the values we care about are built into its utility function, then all of its choices about, in fact, we can even make systems that don't mind being shut off if we carefully build that into its utility function. Yes?
How about if it changes its own utility function?
Well, remember this argument here that it's both a good thing and a bad thing that it doesn't want to change its utility function because it thinks about that action, changing its utility function. Its future self now does something different than it would do because its utility function is different. And so from its current perspective, that's a terrible thing. I mean, imagine that your values involve living you know, a rich life, meeting lots of people and so on, and you're thinking about smoking crack for the first time. You sort of envision yourself going down the road and becoming addicted to this drug, and maybe you'll be in absolute bliss as a crack addict, but from your current value system, that's not a very positive future, and so you restrain yourself.
Like mutations?
Mutations is a big problem, and the systems will understand that as well. And so they will go to great lengths, particularly around the utility function, to prevent them from accidental change. And so all the kinds of techniques that we use today to have error correction and error detection, these systems will have an incentive to do as well. And then as we build the first systems, of course, we want to be very careful. And so systems that are extremely reliable, especially in the critical parts, will be of great importance. Yeah?
See, I'm overstating the problem. I mean, you had me in the first part of the lecture, and I understood the self-improvement, and you went over into this excursion into potential technologies like nanotechnology, and now you're talking about human values. Aren't you overstating the problem?
I think it's a natural line that where we are today in software is a terrible place. The natural way to improve it is to make systems do more of the work themselves. As we follow that line a little further, they become autonomous, and then they will have actions in the world that are guided by values, and we better make sure those are the values that we care about. So it's a broad picture, clearly, and it's not something that's going to happen tomorrow, but I think that we need to be thinking about the end point of where we're going as we move, you know, as we start moving in that direction. Yes?
There's a whole, it's kind of hard to even know exactly where to start, but you realize that economists don't, that you know about revealed preferences in economics. In other words, economists don't really believe they know what people's preferences are. The only reason they know what their preferences are is because of how they act.
Yes.
So basically beliefs and preferences aren't causal in economics or in a lot of psychology or sociology. So you're talking about all these things as causes, but there's no way that, I mean, that's just fairy tales. I mean, how do we know that intentions, beliefs, and all these things do anything? I mean, how can you model something that no scientist really even believes exists?
We have to remember that people are not rational agents. And so we...
well, I mean, that goes without saying. I mean, that's ridiculous. Nobody has believed that forever.
Right.
But,
so you were saying.
What you're doing is you're making a system where you're talking about this hypothetical rational agent, this idea that that there's some relationship to some sort of atomic decision-making process that threads its way through thing. And there's no evidence that exists. No one ever believes in that. It's like this. It's kind of like a 50s or 30s, like almost positivist view of the world that has been. I can't imagine where you're getting this. I mean, have you read Coase or Williamson?
Sure.
I mean,
absolutely.
the microeconomics. You're saying you're putting the microeconomics stuff from the game theory stuff, and it's like you're just kind of picking from all these different kinds of things and throwing them all together, and it doesn't make any sense.
Economics gives a rational basis for making choice in the face of uncertainty, and
some economists do talk about that. Yeah.
I mean, in the kind of objective framework,
Well,
like
no,
software.
you gotta understand, it's a complete circular thing in economics. Economics, it doesn't predict anything because of the fact that the only way you know what a person's preference was is what decision they made.
Yes.
In other words, it's after the fact. You can't, the preferences are a consequence of what people do. But you're making preferences have a causative, be causative.
When we build these systems, we will build them with some goal in mind. In the case of the software system, the goal is to solve
But they're
problems
your
efficiently.
goals.
Yeah, absolutely. And we have to choose them carefully, is the basic upshot. We can talk, let's talk more about it after.
Yeah.
Yeah.
Yeah, there's one reason why these systems won't use meta computation and rational and utility-based design to improve themselves. And it's because I have patents on it.
Of course, they have to respect patent law for that to be the violation. And then if they respect patent law, they now have a strong incentive to find ways to work around it. So, right. Yes?
When you talk about agents being intelligent, and then you say that, we are the ones who are going to actually define the utility function.
Yes.
I really don't think that if you place limits on the utility function that it will actually be intelligent at all. Because you're constraining it to a specific problem for which you want a solution. It isn't general intelligence at all. The only way it will truly be intelligent is if it can actually modify its own utility function and find another set of, let's say, solutions or problems that it needs to attack.
Well, remember, the utility function is saying what it wants to do. It's not really saying how to do it. And so, if you give it a task of, say...
so you have a task solver, you don't have general intelligence.
Yeah, though if you wanted it to apply to, say, understanding natural language, to understanding vision, to manipulating robots...
then you have to allow it to modify its utility function.
No, you would choose a utility of, recognize this object. Here's a bunch of examples. Excuse me?
Then you just have a broader task solver.
Yes, exactly.
So no matter what you do, if you define the task, you would just have a task solver.
Yeah.
You won't have general intelligence.
Well, I mean, it's a philosophical issue of what is general intelligence beyond the ability to solve problems.
For sure, but it also includes the ability to choose new problems to solve, which is not the ability that you're giving to this system.
Though I would claim that you tell me how it is that you choose problems, and we can encode that in a utility function. So, so I don't think that that's a fundamental limitation, but I think it's a very important point that that you have to choose what you want these systems to do. And here I've been focused entirely on the question of writing more effective software and building more effective hardware. And that's a very restricted class of problems. Much of the same technology applies to more general problems, but you're right, that there are lots of interesting questions to have. Yes?
Yes. I've heard this line a couple of times before. Linott was talking like this back in the 80s. Remember how AM and Eurisco appear to work?
Sure.
So you know that one. Yeah. And so he had the first self-improving system along these lines. And then there were the neural net guys who were trying this. And Koza at Stanford has been beating on this problem for the last 20 years and making some progress. The problem is that what happens with all these things is you have some utility function, and you optimize for a while, and you reach a point where you're at a local maximum. And nothing you can try at that point, the space that you're searching, none of your neighbor areas help you. And you can't find anything that makes things bigger, because the only way to get better is to make some drastic change, which is not obvious. And you're in some huge multidimensional space where you can't find it. What seems to happen in practice is everybody who builds a self-improving system has something that basically maxes out within a day of crunching. And more compute power won't help. The comment I made to Koza's group like 15 years ago was, eventually somebody may crack that problem, and there's a Nobel Prize in that one. But so far nobody has. But merely throwing compute power at the problem will not help, because we have things that are maxing out already. You can make them max out faster, but we are missing some key insight to make self-improving systems actually work. And I haven't seen it yet. Do you have it?
Well, the systems you talked about, many of them are subject to local maximum. Things like neural networks have a very restricted form of change that can happen. Typically can only change weights in a very incremental way. Those can get stuck. The Eurisco is more interesting, but none of those systems really had a model of themselves. If the system has a full model of itself, then it has potentially any change, any dramatic, huge leap through the space it designs. It can make it in an instant. If it can prove
of something that's actually working, or is it purely speculative?
We're not announcing any products at the moment, but it's a general class of designs that is a possibility. And clearly they need to be proven, definitely. But the consequences and the behavior of this type of system can be analyzed before actually seeing any of it working. Yeah?
I have a question regarding a basic assumption here. You're looking at a particular class of systems, but there's an assertion that all intelligent systems are in that class. And ecosystems is one that you explicitly mentioned.
Yes.
I think ecosystems clearly are problem solvers. They've created intelligences, for example.
Yes.
But I don't see how an ecosystem that has entities in it with utility functions are ones that tend to act as though they have utility functions, give or take, the sorts of considerations that economists have been studying. But the ecosystem as a whole, I don't see a utility function there.
Well, there's a whole lot of research these days on how larger systems emerge out of smaller components. And I think there is a general pressure for the larger systems to, there's sort of a non-zero-sum gains that come to make the existence of a cohesive group which takes actions in the service of its components. And I think all of the pressures, to the extent that that group can modify itself and can model itself, then the economic pressures are going to come in to have it try and get rid of vulnerabilities. I think you're absolutely right that many existing systems have those kind of vulnerabilities. I think you look at like corporate structures, often information flows get stuck in crazy little loops, or even, you see the dynamics even in a couple where sometimes, one person will get angry at the other one, will get angry at the other, and you sort of get these vicious cycles of which sort of burn up resources, and they're not in the interest of anybody. And so those can be viewed as vulnerabilities in the overall system. And so to the extent that the agents are intelligent and have a model of the overall system and the capacity to change it, they're going to want to try and get rid of those things. And I totally agree that today's ecosystems, though many, like this resource balance principle, there's an exactly analogous thing in ecology that describes sort of the balance between different species in a particular ecological niche. And so and I think you're absolutely right that there's a very, very interesting theory about when you have multiple agents interacting, what happens in that situation. And everything I've been saying here is absolutely right, taking the viewpoint of a single agent that's making decisions about its own structure.
My concern is that I think there may be a wrong turn in thinking about these issues as soon as you say an AI and it, which presumes something about the nature of the problem-solving system.
Yes.
That's my central point.
Yeah. Point taken. Yes?
So, go back to mutations.
Good.
Speaking of it.
Yes.
Assuming we can solve the problem of natural mutations, what about malicious mutations?
Yeah, malicious. Dealing with malicious things is very important. There's an organization, Eliezer's here in the back, called the Singularity Institute for Artificial Intelligence, which is trying to ensure that the consequences of these kinds of systems are immune to malicious agents and to accidental, unintended consequences. And it's one of the great challenges right now, because if you assume that this kind of system is possible and that it has the kinds of powers I was talking about, it can be used both for great good, but also for for bad purposes. And so finding a structure which is stable, and I think I agree with Eric that the ultimate kind of solution that makes most sense to me is essentially to have a large ecology of intelligent agents and humans, such that and a kind of a constitution that everybody follows, and that humans probably will not be able to monitor AIs because they're going to be thinking faster and more powerfully, but AIs can monitor AIs. And so if we set up the structure so that each entity wants to obey the law, wants to follow the Constitution, wants to respect all the various rights that we were to decide on, and if somebody starts violating the law, that they have an interest in stopping them from doing that. The hope is that we can create basically a stable future society of these kinds of entities. But that's the thinking is just beginning on that, and I think a lot of input is needed from economists, it's needed from psychologists.
I can't stand economists.
I see. Oh, okay. Which letter? You were a psychologist?
I was a sociologist.
Sociologist. We absolutely need sociologists. As well as computer systems engineers. I mean, we really need input from a wide variety of disciplines. Because, this is technology that, people disagree on the exact date. Is it 10 years? Is it 100 years? But somewhere in the next coming decades.
When the patent expires.
When the patent expires. What is it, 19 years? So, yeah, they're critical questions, and we really don't have the theoretical framework to handle it at this point. And so, lots more input is needed. Yes.
So going back to the infinitely powerful computers, and you could essentially imagine you build a huge lookup table, that's the best utility maximizing thing. But then, what's your response to something like John Searle's Chinese room argument, in terms of, you've built this extraordinarily powerful computer, but does that actually have the ability to, going back to the general intelligence question, I guess, what's your response to the Chinese room?
So everything I've been talking about is intelligence. The Chinese room is about consciousness, and about what does it mean for something to know Chinese. And nothing I've said touches that argument at all.
So you can have intelligence without consciousness?
Yeah, absolutely. I view intelligence as just the ability to solve problems using limited resources. And this is the class of systems that I think does that most effectively. How that relates to human thought, to the human experience, to consciousness, I think is a very interesting thing, and probably the development of this kind of technology will shed a lot of light on that.
And do you think you can have general intelligence without consciousness?
I believe so. That one is probably more. I think probably almost everybody would agree the kind of thing I'm talking about is theoretically possible. I think others, I know Steve probably doesn't believe that the kind of recognition of objects that we do, that sort of qualia, the feeling of observing something, that's possible in this kind of system. I'm pretty agnostic on those kind of questions. Yes?
Yeah, just for a vision, I take a bit issue with the idea that humans are not self-improving or not at the same rate as you can improve AIs, because I don't necessarily believe that as we have, know what we have an explosion of information in systems biology, and most of it is, driven by this quest for self-improvement, beating the disease and things like that.
Yes.
So the question is really, where do we put our energy, or rather, as I said, it doesn't have to be a competing effort. You could, as you said, have an ecology of humans interacting with AIs,
yes,
as we already do with our computer work.
Yes.
And so I see that you should have a vision on that as well, on the self-improvement in humans, and actually some sort of timeline for that.
Yeah, I think that's...
And how we have these interactions going, how you can use your AIs for this goal.
I think it's a very interesting area. In fact, there is a huge self-improvement industry. I think it's about $8 billion a year right now.
It's constrained by evolution.
Can you summarize the question?
So the question was, humans aren't able to self-improve at the level that I've talked about here, but nonetheless there's a desire and a strong intention for doing that.
You said constrained by evolution. I said not necessarily. It's not just about improving our minds anymore. It really is about improving our,
improving our
ourselves.
bodies, yes.
Right?
And that is there a vision
and our
for...
material, structure.
Is there a vision for how to include human self-improvement along with this kind of more technological self-improvement? And the two come together, though I think that the ethical issues start getting really big. Right now we have huge debates raging about stem cells and abortion. When you can choose the genome of your child, when you can, certainly repairing diseased organs, I think nobody would have qualms with that. What about, oh gee, I don't want to have a conscience anymore, so I'm going to modify my brain to have no conscience. Should that be allowed? Should we restrict that? I think a huge number of ethical issues arise, and sociology is going to have to rise to the task of humans with these great powers, and we don't really have the moral framework within which to make these decisions.
I mean, is the tenure of your argument, made a very good initial argument for use of formal methods. You made some good arguments, I felt, about self-improving systems. Now you seem to be raising the question of whether or not we should do it at all.
I don't think we have the option of not doing it.
So why not just proceed?
I think we need to do it very carefully. That if we want the outcome to be something that is I think the potential upside is huge. An enormous benefit to all of humanity, solving many of today's problems.
But in the 1960s, wasn't there a lot of concern about just computers in general, taking over the world, and isn't there a certain element of alarmism? Do we really have to worry about those?
Well, I mean, these arguments are not alarmist. They're just, rationality. You can disagree with the mathematics of it, and maybe it's not. Maybe you can find a different setting in which the argument isn't applicable. But it's not just sort of a kind of knee-jerk fear. It's based on a particular mathematical analysis of the situation.
Do you have more slides?
No, that's it.
Then I have a question.
Yes.
Do you think formal methods as we utilize them today are adequate to provide the inputs for this kind of system? Formal methods are at least as hard to do as programming, and at least as hard to do correctly.
Well, I would disagree with that, because you can state, like you look at the bugs in the first 7 horrible systems that I mentioned. Those are all things that in a one-line formal method you could say, no floating point errors. And, and your program has to provably not have that kind of error. No type error, no stack overflow. Security issues are harder to model, but there's a big bunch of research on how to do that. And also, if you I'm not a huge fan of these particular spec languages that I mentioned. I mean, I think there's some great important ideas in there. I've got my own language, and I've been writing lots of specs. And if you get the right abstractions, it's actually pretty quick. You can write a chess spec in a page and a half, something like that, much more quickly than you can write a chess program. The spec for sorting is, basically it has to be a permutation. The numbers have to be in order. That can be a much simpler spec than having to say exactly how you do the sorting. And particularly very optimal algorithms are quite intricate, and the spec doesn't have to worry about optimality at all. The spec can be whatever is best for the human author of that spec. Specs change a very little bit when the problem requirements change, whereas the resulting code can change a huge amount. And the properties that you want to preserve, safety, mathematical integrity, those are often very short things to specify.
Question.
Yes.
So, given that us humans are writing this utility function and writing this spec, and we're inherently imperfect, I mean, is there a way that we can prove that these guys are not going to just run amok no matter what we choose for utility
Well,
function?
if you can precisely define what you mean by run amok, then yeah.
well, could they exploit any imperfection in the utility function that would cause them to run in some way that we do not want them to run? And
that's certainly a possibility, and Eliezer actually has a lot of ideas about how to use these systems themselves in designing the right utility function, because they're going to be able to do it much more effectively than we are.
Okay.
Exactly what the intellectual framework that underlies that is, I think, is still very much in the air, but I think it's a direction that probably is an important one to go in.
Do you think a collaborative improvement of the human entity as well as the mechanical entity would be the ultimate course of events?
I don't know. It makes me very queasy. I don't like, I think, we've had so much experience messing around with ecological systems and biological systems where we didn't quite understand everything and it led to bad consequences. I think we should step very lightly as we consider changing ourselves and biological systems. Clearly there's going to be huge pressure to do that. And how we mediate that line between wanting to create good and not doing great damage, I think, is one of the challenges.
Does it make sense to have part of the utility function be ask us, by some definition of us, are we happy?
Yeah, that's a great possibility, though you have to say exactly who us is and how do you get the preferences of the entire planet, how do you combine it? Does voting work? Voting has all kinds of irrationalities in it, for example. Okay, great.
You sort of talk in a way that once it takes off, it happens by itself. But another possibility is that actually we have to be involved.
Mm-hmm.
And so I have a question of how would you educate? I mean, with our present education, we don't achieve this. So what will our education need to be so that we can be involved, will be sort of effective? Even if not all this automatic thing, but anyway, better ways of coding, getting programs that are reliable instead of having all this bugs. So what do you see for needs of areas of education for people like us?
Yeah, I think that's a really important thing. I think formal methods are very important. They're much more stressed in Europe than they are in this country. I think a lot of mathematics, probability, Bayesian statistics is pretty fundamental to this. A lot of if these systems really work the way I'm saying, then much of our interface with them will be through our values. And it's the kind of thing you were saying. We need a language for thinking about values and thinking about sort of moral dilemmas. They're very simple. If you look on the internet for trolley problems, they're very simple moral dilemmas that the philosophers don't agree on. Huge raging debates about extremely simple little tasks. And so how we're going to incorporate the values that we all care about and make sure our technology supports the kind of living we want in the future, it's a challenge. And I think we need an educated populace and we need awareness of the possibilities. Yes?
You talked about all the challenges in writing the utility function and incorporating all the values in the debates. But using this line of thought, does that mean before we can even hit go on the simplest self-improving program, we have to have solved all those problems?
It's a very interesting question. I'm hopeful, and I think a lot of people working in this area are hopeful that it'll be possible to design sandboxes little enclosed things that we can be very sure will be safe. Maybe having human intervention at several of the steps. System isn't allowed to actually change itself, it just proposes a change and a person okays it, something like that. It's very tricky when you're dealing with intelligent systems though, that especially if they have incentive to get around any blocks you put in front of them. And so we really need a mathematical theory in order to do careful design in that. And there is a fear amongst a number of people that if you do it wrong, that there could be a runaway effect. And so understanding, I think, is what we really need.
Now, when someone builds something, I guess, like the botnet, that they're really targeting getting money or they're targeting something bad, have you thought about how to stop one of these things in case something does run amok?
Well, you know, there have been, I forget what they call them, viruses that people have written that go out and infect machines whose job is to find other viruses and get rid of them. So they're supposedly, you know, positive viruses. Right. Unfortunately, the actual consequences of them, for the most part, has been that they don't quite work right and they end up breaking lots of machines. And so it might be that a very carefully thought out and fundamental basis for that type of system would be a good way to protect against rogue agents. But yeah, a lot of research is needed to understand that situation better. Yeah.
Just say for the sake of argument, we didn't care about a runaway situation. That was the point. We just want to give birth, and then what happens to us happens to us.
Leaves me chilled. I mean, that's sort of the theme of many dystopian science fiction novels and movies. You know, one thing that's scary is some person might have that attitude, and if the technology is easily enough available, we have to make sure that a single small group can't impose that kind of a decision on the rest of us.
I think with that we might take one more question, and then thank you for your interesting thoughts. Is there one more question? We've solved all the problems.
There we go.